Yeah, so I want to remind everyone that hasn't yet signed up on the Google Sheet to sign up for a Tuesday talk or two. And Peter, take it away.
Yeah, I mean, I'm giving this talk today because a Reed bullied me. You have to sign up and you should be one of the first ones. So here we are.
We want to start with the great speakers and set the bar high.
We should reevaluate that after the talk. Okay. So today I'm going to be telling you guys about algorithms for solving random and semi-random planted constraint satisfaction problems. This talk is going to be based on two papers, which are joint works with Arpan, Venkat, Tim, Pravesh, and Andrew. You may see Arpan and Andrew around, by the way. They usually come to the Monday seminars. You can say hi to them.
Right.
They're not here today. No, they don't come on Tuesdays. Okay, so this talk is going to be about constraint satisfaction problems. For example, like k-sat, which you're probably familiar with. Here you're given as an input a set formula, which has n variables, okay, and n clauses. And we also call the clauses constraints or equations. And in a k-sat formula, every clause is just an or of k literals, where a literal is a variable or its negation. So this is a 3-sat formula. You have x1 or not x2 or x6. That's a clause. Okay. And more generally, in an arbitrary Boolean k-CSP, you have some predicate p, and you feed in for each clause, you feed in k literals to p, which are the variables or their negations, and you want to check that p evaluates to 1 when given those inputs. Okay. And the central question here is to decide if the instance you are given is actually satisfiable or not, meaning is there an assignment to all the variables that will satisfy all the constraints. Okay, and this is a classical problem that we now know from the Cook-Levin theorem. It's a very classical result. This is NP complete in general, or k-sat is NP complete and other k-CSPs. Yeah.
Do you assume every clause has exactly k? Or
yes, exactly.
Okay.
Let's just go with exactly k for simplicity. If you added more clauses, what's going to happen or clauses with at most k, what's going to happen downstream is like, if there are enough of size exactly k, that's going to be the dominant thing, or else you can just like basically throw them all out and work with the k-1 stuff. Yeah. Good. Yes, but let's just think of it as exactly k. So here k-sat, it's NP complete. This is hard. You can't decide if phi is satisfiable or not unless p equals NP. Okay. Okay, fine. So maybe our goal here was a little bit too ambitious. You're trying to decide satisfiability or not, which is saying, can you satisfy all the constraints or at most, n-1, right? And that's just like a very small gap. Maybe if I just say, I'm giving you an instance and you just try to satisfy as many clauses as possible, maybe if I give you something that's like, you can satisfy all the clauses, you can maybe satisfy like 1 minus epsilon of them or something, right? So you could try to relax our goal and say, let's just try to satisfy as many clauses as we can. And this is also hard. Okay, so there's some works on probabilistically checkable proofs, which came into this field of hardness approximation here. And basically, Hostad's PCP from 2001 says that it's NP hard to even find an assignment that satisfies a bit more than 1 minus 2 to the minus k fraction of the clauses. So think of epsilon as like a very small constant. So this term here, the 1 minus 2 to the minus k, is coming from the fact that if you pick a random assignment, this is the fraction of clauses it will satisfy. You can see this because the OR function, if you just check all 2 to the k possible inputs to the OR function, all but one of them will actually pass. So this means, if you pick a random thing with probability 1 minus 2 to the k, you will satisfy the clause. And so what this is saying is that if you output a random assignment, this is what you will achieve, and it's NP hard to really do anything better than this. Okay, so this already looks pretty bad. There's not much room for designing an algorithm here, but there's one last parameter we can try to play with, which is that if you look at these hard instances, they're very structured instances, and moreover, the number of clauses they have is about actually order n or maybe order n log n. Okay, so the hard instances have basically linear number of clauses in the variables. So maybe you look at this and you think, okay, if I go to maybe n squared clauses, the problem may become easier. So you could try to study, again, how does the hardness depend now on this additional parameter, which is the number of clauses. Okay, and so I can plot this on this picture here, where on the x-axis I have the number of clauses in my instance in log sleep. the y-axis, I have the runtime of the algorithm in log scale. And here now we're going to have to assume something a little bit more than p not equal to np. We're going to have to assume something like, say, the exponential time hypothesis in order to get a more fine-grained control over the runtime here of the algorithm. But if we do assume the ETH, there's some PCP-based results, initially Moshkovitz-Raz, and now this recent result of Bafna, Minzer, Bias, that basically show that, there are instances even up to n to the k-1 constraints, it actually requires 2 to the n over polylog n time to even beat the random assignment. So I'm not going to be too worried about this polylog here. I'm going to basically just say this is exponential time.
I mean,
Yeah.
if the number of clauses is like n to the 1 minus epsilon, there's still exponential time algorithm.
N to the 1 minus epsilon.
Yeah, like on the left-hand side of your,
Here?
no, to the left-hand side. Yeah, to the left of n, there's an algorithm which is just like 2 to the number of clauses, right?
Yeah. So I'm not going to worry about, sorry. I'm not supposed to.
I'm just wondering, I don't know what this red line is, that's what I'm saying.
Oh, the red line.
It's like n over polylog n.
Maybe you should just not worry about this part of the
Okay.
picture. Yeah.
It should
Yeah, maybe I should.
Yeah, it should not, it should be a linear thing going down to 0.
Yeah, okay, yeah, you're right, it shouldn't be. I guess in this talk, every instance is gonna have much larger than n clauses. I just kind of put the line there.
Start the x-axis and then.
Yeah. Okay, yeah, so we're ignore this picture.
Okay. From now on, I will.
Yeah.
For the rest of the slides.
This picture is gonna appear a lot, but actually.
Okay,
But
all right.
more or less when I start talking about the problem, it's like not even gonna be defined in this regime. So like,
I mean, it is, but okay.
well, yeah, but like the specific distributions. But like,
Okay, yeah, you haven't gotten.
I haven't gotten to where I'm gonna
Sorry,
go, but when I
sorry.
get to where I'm gonna go,
Okay,
you'll
okay.
realize the problem like doesn't even
Okay,
make sense.
I will.
Yeah.
I will not look at that anymore.
Yeah, good, okay. Please don't. Yeah, so basically, once we go beyond here, this is very hard. All the way to n to the k-1 constraints. On the other hand, if I give you way more constraints, like n to the k constraints, the problem becomes easy again. And there's a reason for this, which is that, well, basically here I'm giving you a constant fraction of all possible constraints, because if I give you a k sat instance, there's only n choose k or order n choose k possible constraints. Okay. And so then
I think this is true for approximation, right?
this is for approximation.
Yeah,
exactly.
okay.
Yeah. And then in the middle here, you can also get algorithms that kind of go between these two points, right? So basically 2 to the n of the delta time needs n to the k minus delta constraints, and you got to, essentially matching lower bound, up to polylog factors or something. Okay. So there's really not much you can do here in terms of worst case instances. So a pretty natural way to just try to go around this worst case hardness is to just now pivot and study random instances. And this is just, once you go to random instances, all these worst case hardness results go out the window, and there's again no reason to believe that you can't design an algorithm. And this is a very standard way of avoiding all these worst case hardness results. There's a whole book on beyond worst case analysis, and that's exactly what this is. Okay, so your input here is now a random Boolean k-stat formula, and your goal is to decide if it's satisfiable or not. And now you run into a rather annoying issue, which is that if I give you more than n constraints, this is unsatisfiable with high probability. So if you're just trying to decide if it's satisfiable or not, this is very easy. You just say, always declare it to be unsatisfiable, and you're correct with high probability. On the other hand, if I give you fewer than n constraints, the instance is satisfiable with high probability, and moreover, it's just completely trivial to solve. Okay, and there's another reason for this, which is that if I'm at less than n constraints, you expect each variable to only appear in one clause. And then that just becomes very easy. You just pick it to be the value that will satisfy the clause. I should mention that if you are very precise about what constant is appearing in front of the n, which I am not going to be for this talk, there is an actually interesting regime where you can get things that are like satisfiable with high probability, but seem hard to find and satisfying assignment, and so on and so forth. Okay, but for this talk, I want to work in the regime again, where m is going to be much larger than n, maybe at least n polylog n. And so there are two ways to get around this problem. Okay. The first thing is you can ask that rather than trying to decide if it's satisfiable or not, you can ask to require a certificate of unsatisfiability. This is the refutation problem that Oliver talked about yesterday. And the thing I want to focus on today is the planted version of the problem, where you now sample from a different distribution. You don't pick a random distribution. You sample from a distribution that's supposed to mimic this random distribution, but still be supported only on satisfiable instances. Okay, so what you're going to do is you're going to generate the instance phi along with some planted assignment x star that will satisfy phi. So like it's a joint distribution on those two things, and then you'll just be given phi as input. Okay.
Here, are we thinking about entirely satisfiable or one minus epsilon satisfiable?
I think just for simplicity on my slides, I'm stating everything in terms of exactly being satisfiable, but actually all of the results will hold for both regimes. Okay, so I'm actually going to talk about refutation today, nonetheless, even though I said this talk is about planted CSPs. Okay, and there's a reason for this, which is that the refutation problem we know more about and we studied it first. And it's in some sense easier to work with because this input distribution is this nice, fully random distribution. Okay, so you'll see first the results for the refutation problem, and then you'll see that what we're doing for the planted version is trying to prove basically all the refutation results, but now for this new algorithmic task. Okay, so that's the plan for today. I'm going to first tell you about refutation, then I'll tell you about the planted CSPs, then we will have an intermission, a little break. And then when we come back, I'll actually go onto the board and start proving some things for you. Okay. Should also mention that so far I've been talking about random CSPs. Eventually I'll get to semi-random CSPs, which were also mentioned yesterday by Oliver. And essentially what these are going to be like distributions which are supposed to have some amount of randomness in them, but also be some amount of worst case as well. Okay. So let's get to refutation. So here the input is again this random Boolean k-set formula. Okay. And the algorithm is supposed to output one of two things. Either it declares the instance to be unsatisfiable, or it says, I don't know, it's allowed to give up. Okay. And we want it to have the following guarantee, which is that for any input phi, even a non-random, like worst case input phi, if the algorithm indeed declares the instance to be unsatisfiable, then it actually is unsatisfiable. Okay, so this is a zero error guarantee. There is no, the algorithm is not allowed to make a single mistake here. And in this way, we say the algorithm is certifying unsatisfiability or refuting the instance. These are the same thing. And because if the algorithm outputs unsatisfiable, you know for certain now that the instance is actually unsatisfiable. Okay. So this gets rid of that trivial algorithm that just outputs unsatisfiable with probability 1, because clearly, even though a random formula is unsatisfiable with high probability, there still are satisfiable instances in the support of this distribution. So that will not satisfy this guarantee. On the other hand, there is a trivial algorithm satisfying this guarantee, which is the one that just outputs I don't know all the time. So we want this algorithm to have some functionality, which formally will just want it to refute a random instance with high probability. Okay, so you sample a random instance, feed into the algorithm, and hopefully with high probability over the draw of the instance from this random distribution, the algorithm actually outputs unsatisfiable. I guess formally I didn't tell you what a random instance is, but it's really exactly what you think it is. You draw each clause independently from the set of all possible clauses. With or without replacement, it actually doesn't really matter. Okay.
Here, just I have a question. I guess another way you could rule out the trivial or get rid of the trivial algorithms, you could ask for your error probability to be lower or something like that. Like here, you have error probability 0, right? And I guess the trivial algorithm, I don't know, it depends on how you set up the distribution, will have some error probability. Is that studied at all, or?
This thing could say unsat, like if it.
If you say it's unsatisfiable with like always, you are right with like probability exponential and minus like m over n or something.
Right, yeah, I'm saying.
Yeah.
But like.
So you could try to make this like even better, and then you again recover something, but you're like really, I don't know, you're sort of, you're really like haggling over the epsilons there. Like,
I just mentioned it because like I guess like in the stuff related to like Kolmogorov complexity and stuff like that, people thought the distribution, the uniform distribution was uninteresting because it's like a random string will have high Kolmogorov complexity with very high probability. But then there was this paper by Raphael Pass and Yanni Lewin said, actually, hey, this distribution is really interesting. You just have to consider the error probability better.
Oh, I see. Yeah, it's possible. I don't think anyone has really thought too hard about this. I suppose like some of those works that are really trying to nail that constant down in front of the n, like you pick m equals c times n, where the c is like, it's like 2 to the k natural log 2 plus like some very specific thing. That is sort of getting into this regime where you really need to compute this like tail bound on your turn-off thing, like very, very precisely and so on. Yeah, so there are some things that are kind of in that vein, but formally, I think no one studied that. Good. Okay, yeah, so that's our goal. We're trying to refute a random instance with high probability. There's two things we additionally want. You know, when you're designing an algorithm, we want to minimize the runtime. Kind of duh. But the other thing is we want to minimize the number of clauses that we are given. And you can rationalize this by thinking, you know, if I give you more clauses, the instance becomes kind of easier to see that it's unsatisfiable. You're given more constraints. So ideally, if I give you more clauses, you know, your runtime is going to go down. So there's actually going to be some tension here. If I give you fewer clauses, your runtime will probably go up because it becomes harder to check that the instance is unsatisfiable.
Peter, if you get more clauses, can the algorithm just kind of subsample to get the right amount of clauses and then work for a specific m? Like, is this also a formal?
Yeah, I guess, but like, I don't know, then you're kind of like throwing out all the information, extra information you give. Like formally, if I give you more clauses, it's yeah, as you said, it's only makes the problem easier. But there's like other versions where I don't want to just output unsatisfiable. I want to like bound something, like say you cannot satisfy more than like 1 minus epsilon fraction of the clauses. And there, like if you can do that for a sub instance, then you could like partition your clauses into these sub instances and then refute each sub instance individually. In fact, the algorithms that we come up with do something like this sometimes. So this is not like a.
But anyway, you don't have to say minimize m. You say for each m, I want the best one.
Yes. Basically, what we really want to do is identify the optimal curve here. Yeah. In fact, you'll see now when you identify the optimal curve. Okay. So, you know, here is the kind of worst case picture here. Again, Ryan, you know, refutation doesn't make sense down here anymore. Okay.
The algorithms.
The problem of refutation doesn't even make sense.
No, it makes perfect sense.
You can say failed.
There can be unsatisfiable things like concentrated clauses.
No, but not a random one. Like,
Okay.
yeah. Like refuting a random instance down here doesn't make any sense.
That's, I mean, with exponential.
Okay, Ryan, okay. Do you want to haggle over the thoughts? All right, yeah, so, okay, so the first algorithm I want to mention is this work of Allen, O'Donnell, and Wittmer from 2015, as well as this work of Kojaglan, Goddard, and Lanka. And essentially, these two results show that with only n to the k over 2 clauses, you can get a polynomial time refutation algorithm. Okay. I guess I'm suppressing polylog factors, and I'm going to suppress polylog n factors for the entirety of the talk. Okay, so if you're worried that this is only n to the k over 2 and not n to the k over 2 times polylog n, don't worry about it. I think actually for this case, you can remove the polylog, but sometimes you won't be able, or we don't know how, and other algorithms are going to state. Okay, so this is already like way, way better than this n to the k thing. It's even better than this n to the k minus 1 hardness that we had in the worst case. And there's also an algorithm that will kind of smoothly interpolate between running an exponential time at n constraints and running a polynomial time at n to the k over 2 constraints. And this is sometimes called the spectral threshold because these are spectral algorithms. And it gives you like this kind of full curve here. Basically with 2 to the n to the delta time, you need n to the 1 plus 1 minus delta times k over 2 minus 1 constraints, which you can observe, you know, I plug in delta equals 1, I get exponential time, and then this thing goes away and I get n clauses. I plug in delta equals 0, and I get, you know, 1 plus k over 2 minus 1, which is k over 2. And that's polynomial time. I mean, okay, delta equals 0, formally constant. Remember, there's polylog factors hidden everywhere. So the polylog, polynomial time here. So, okay, so you can get this whole curve. Of course, we're interested in the optimal curve, so we'd like to also prove lower bounds here. And there is a matching lower bound, at least for sum of squares algorithms coming from this work of Kothari, Mori, O'Donnell, and Biddle. Okay. These are unconditional lower bounds, I should say. But they are in a restricted computational model, or that is, you require your algorithm to be this sum of squares algorithm, which is the reason you can prove, of course, an unconditional lower bound without proving p not equal to np. So yeah, of course, when you're proving one of these lower bounds, you should always be worried that maybe sum of squares is just a really bad algorithm here, so your lower bound doesn't actually mean anything. Turns out SOS is a good algorithm here. This algorithm is SOS, so is this, and so is this, or at least they're captured by SOS, and you can make them sum of squares if you wanted them to be. So the lower bound is more or less capturing actually all our best known algorithms here. So this is, at least in my view, some reasonable evidence that we're hitting the right curve. Okay. So this is the picture for random k-sat. Of course, the picture gets slightly more complicated if I took an arbitrary predicate. And essentially what happens is you have to define something called the predicate complexity, which is the smallest integer t, such that there is no t-wise uniform distribution supported on satisfying assignments to p. I guess if you write p in the ±1 basis, you could equivalently view this as if you take a distribution over assignments, local assignments here, over satisfying assignments to p. That is, you want every Fourier or you want the smallest non-zero Fourier coefficient to be like t, have weight t. Okay. I guess S has to be non-empty because the empty set also has non-zero Fourier coefficient, just because it's a probability distribution, so things sum to 1. Okay. But so that's what this means. And of course, if I'm calling this predicate complexity, you can imagine that this is going to actually determine somehow the number of constraints you need. And this is the case. Okay, so the real picture for random CSPs looks like this. Basically replace a k with a t everywhere. And that's what happens. So you only need n to the t over 2 constraints if your predicate has this no t-wise uniform distribution. Just to connect this to k-sat, k-sat does have a ky or has a k-1 wise uniform distribution supported on its satisfying assignments, but not a k-wise one, which is why its predicate complexity is k, and then you get n to the k over 2. Okay.
Fantastic. The exclusive OR.
With what?
Exclusive OR.
Exclusive OR, yeah. Exclusive OR also has k, right? XOR.
So,
Yeah,
so
KXOR also.
yeah.
So KXOR, the way I've defined things as like refuting as determining like value less than 1 is easy because it's linear, though if you wanted to make it like value less than 1 minus epsilon, it's again like a meaningful problem. Yeah. Okay, so this is like the whole picture for random CSPs. Though, okay, so I basically told you that this is solve problem, worst case couldn't do much. Average case, we had sort of some threshold where we got an algorithm, and we also knew that kind of below this threshold, we don't have anything of it. Okay. And this means we've accomplished our goal of designing essentially, like our optimal algorithm to refute a random instance. But there's a little problem here, which is that this is not like actually our real goal here. Like our real goal was to try to solve k-sat more generally. We couldn't do it in the worst case, and random was just like one way to get around the worst case instances, right? What you really want is to try to be refuting as many instances as you can. And so in particular, if you take a random instance and you add like a little O of 1 fraction of like adversarially chosen clauses or something like this, you would like to refute those instances too. I mean, adding the small amount of clauses should intuitively like not affect your algorithm in any meaningful way, and so on. So you should be able to refute those. And so you can ask, are there algorithms the algorithms that we came up with for the random case able to handle these perturbations in the model? Are they robust to them, or are they really overfitting to kind of the specific input model that we chose? And of course, if I'm talking like this, the answer is that it is overfitting. And so the algorithms for the random case will not work here. But what goes on is you add these adversarially chosen clauses, And the spectral norm of the matrix that's like somewhere deep in the algorithm goes kind of wild and gets way too high, and now your algorithm doesn't refute anything anymore. Okay, so these algorithms are not robust, and you can think of this as really, we shouldn't stop at random instances. That's just one extreme here where we have a fully random instance. Worst case was another extreme, and we can try to study like what's happening in the middle here. And this is exactly what a semi-random model is. These were, I guess, pioneered by these works of Feige and Killian, and then Spielman and Tang, and also Feige later. And the overarching idea here is you take one of these algorithms for these fully random instances and you try to make them work in cases where the input is like less random in some structured way. Okay. You saw yesterday actually a great example from Oliver as to why this actually matters in various applications. Okay, he had something with these NC1, NC0 pseudorandom generators. And yeah, I mean, he really needed the thing to be semi-random in order to make his proof work. Okay, so there's a lot of different semi-random models, but I'm talking about CSPs today. So let me tell you what a semi-random CSP is. Okay, it's going to be chosen in two parts. The first is you pick a hypergraph H, which specifies variables that appear in the clauses. Okay, so I have, hyper edge 1, 2, 6. That means x1, x2, x6 will be in the first clause. Then I have like 8, 15, 12. I have x8, x15, x12, and so on. And then to finish specifying the instance, I have to tell you which variables are negated or not, and you just choose those randomly, and that gives you your semi-random instance. Okay, so there's two parts here. You can think of really any CSP as being broken into two parts. There's the hypergraph and the literal negations. In the fully random input model, these were both random. In the semi-random case, the hypergraph is going to become worst case, and the literal negations will stay random. Okay, so semi-random is really just like the fully random case, but the hypergraph has now been made to be worst case.
But just for that, for other CSPs.
No, you can do this for other CSPs too. The same thing. You just take your predicate.
So you will negate variables in other CSPs. For some, it makes more sense. But
For some, it makes more sense. Yeah. I mean, yes. For some, it makes more sense than others. Maybe you want to pick your predicate, so this is like a meaningful thing to do. But yeah.
I just have the set predicate and choose on the set.
You could do that too, yeah. I think if that set is sufficiently rich, all the algorithms should still work in that case too. Yeah.
Is that studied though? Like what kind of semi-random makes sense for different predicates?
I think this is the only model I've seen studied, though most of the papers are also mine. So I don't know. I mean, not all of them, obviously. Like this work is studying even a smoothed model where you don't just pick random literal negations. You kind of flip signs, starting from worst case signs, and flip them with some small probability, which then you can reduce to a random case. For example, Feige was particularly focusing on presat, but you can even define it for an arbitrary predicate. Yeah, I mean, there's like other various ways to do something reasonable. Like this paper is about a smooth model for linear programming, where basically, I mean, it doesn't look like this at all. What you do is you're like perturbing those coefficients on the linear equations. And what this paper is arguing is that, the simplex algorithm runs in polynomial time when you do this with high probability.
This is the smooth analysis.
Smooth analysis paper, exactly. So it's
very different.
And then this paper is about, I think, independent set. So there's again, like, you can define semi-random graph models and they don't look like this. So, I mean, basically semi-random is like just a kind of catch-all phrase to say that you're trying to take some of the randomness out in some particular way. Yeah.
Do people study like the probability of negation? Like if it's 0, then it's trivial. If it's 1, then it's trivial. But if it's 1/2, then you get this model.
If it's 1/2, you get this model. If you change the 1/2 to anything, like everything's still, like basically every result I'm going to state will still work.
Well, if it's 0 or 1.
If it's 0 or 1, yeah, it needs to be some constant bounded away from 0. Yeah, constant bounded away from 0.
Anything between 0 and 1.
Any constant bounded away from 0, 1. In fact, you can even get a dependence that will depend on like it's bound away from 0.
Oh.
Yeah. Should be like 1 over that thing to some like squared probably is the actual number of factor of constraints you need. off the top of my head, though I think like the way our algorithms work is we actually lose like some extra factor there because our analysis is probably not quite optimal.
Okay.
So maybe get something like that to the 4. Yeah, morally speaking, yes, these things don't really matter. And this is like kind of the whole point of picking semi-random, okay, is that like you can change your model in these various ways and your algorithm should still work. Okay.
Peter?
Yeah.
Maybe this is a stupid question, but is there reason to believe if the hypergraph is arbitrary that the instance is actually still unsatisfiable?
Yeah, this is pretty easy to see once you just like stare at it. So think of the fraction you will satisfy with a random assignment. This is still not going to change. In fact, the randomness of the literal negations just means that regardless of what assignment you pick, like, okay, the way you prove this is probabilistic method plus union. I should say that up front. Okay, so when you pick your assignment X star and you try to see like how many clauses is it satisfying, it's like local view on each clause is independent and uniform. So then your turn off bound is the same turn off bound. Yeah. So it's clearly unsatisfied. Good. Okay. So yeah, I guess the final thing I wanted to say here is we have fully random in worst case and semi-random sits somewhere in the middle. All right. Okay, so what do we know for semi-random? Well, this lower bound here was for random, so it's still sticking around. And I guess there was this work of Abascal, Guruswamy, and Kotari from 2021 that gets the polynomial time case. And then there was my work, 2022, that gives this full sub-exponential time trade-off here. Okay, so notice it's literally the same picture, okay? Like, the whole point here is that we can take those algorithms that worked for random and then just upgrade them and make them work also for semi-random. Okay, it requires more technical ideas and so on, but the moral of the story here is that semi-random isn't harder to do than random.
It's the same algorithms, more or less.
You just said that it couldn't be the same algorithm because you said the
So-
algorithms are not good for these.
This gets into this like weeds of whether you count SOS as an algorithm.
Mhm.
Because you can technically say that like, I'm running SOS and I compute the like pseudo expectations value and I output that. Okay, how do you prove this works though? The way you prove it is by coming up with a different algorithm and then analyzing that. So in this sense, the RRS work, for example, their official algorithm is to just run SOS, but then they analyze it by giving like a completely different spectral algorithm and arguing that thing works. So that spectral algorithm they give will not be robust to the changes. But SOS will, but the reason SOS is because, we proved it here with a different algorithm. So I don't know, at some level, like calling SOS an algorithm here is like, I don't know, it's just kind of like, it just feels like you cheated a little bit.
It's in a higher degree in the semi-random thing?
No, it's like literally the same degree. In fact, our bound on the number of constraints is actually like better for the semi-random case in terms of the polylog factors. In some sense, like what ends up happening is to do semi-random, you need to like understand the random case better. And once you get a cleaner analysis there, some of the polylogs just like fall off. I guess it actually wasn't this work, my work, that shaved the polylogs. There was a follow-up work of Shea Kotari and Siddharth Mohanty that shaved off all but one of the polylogs, but okay. Yeah.
No, I'm not sure what you mean by SOS is an algorithm or not. It is an algorithm. For any algorithm you give, you have to prove that it works.
Yeah. So
So
okay.
it's, maybe you don't know how to prove that that's what works. Another one.
Sure.
It's an algorithm.
It is an algorithm, but like I don't know. It's like if your proof doesn't extend to the semi-random case, like you don't know if it's
you can
robust.
prove that SOS works by giving another algorithm and another analysis, and then also show that it implies that that's what.
Yeah.
Peter.
Yeah.
Is there a conjectured model which might interpolate between these worst case and even semi-random?
mean, there isn't, but I can think about it, maybe come up with one. Not off the top of my head, actually. I think the simple thing.
This is a binary search between random and worst case. Semi-random was in the middle in your picture.
Yeah.
Now you actually solved it. Now you need to search between semi-random and worst case. Find
Yes.
another.
Yeah. No, you're right. It's hard to formalize because, for example, if you try to pick some of the clauses as adversarial and some of the clauses as not, like what ends up happening is you can make the algorithm work again. But what it's doing is it's like refuting the like part that's semi-random and like it's ignoring the part that's worst case.
It knows which is which.
This follows from like generic SOS magic, where SOS is linear, so you can split the instance into the two parts.
I see.
But the hypergraph underlying this semi-random model is arbitrary. It's
Arbitrary.
So it's not like what you just described.
No. I was talking about the literal patterns. So you could put like, you could have some of your clauses get literally worst case, like literal negations
Oh, I
on
see.
them. Yeah, and others get random ones.
But you can also reduce to subconstant probability.
I think at that point you just lose. Like I think at that point it's over.
Can you maybe allow the adversary to control some negation to every clause? Or something like that?
So that will definitely break the current algorithms.
Which is probably a good thing.
Which is, yes, what you're trying to do is like break the current algorithms, but still make it doable somehow. I'm not sure if that is doable.
One negation.
One negation may be a problem. No, because what ends up happening is you convert this, you'll see some reduction later, where I convert this to a k-XOR instance. Well, rather you do is you take the Fourier decomposition of the predicate, and you get like a t XOR for t going from like 1 to k. And the right-hand side of the k-XOR, that the k-XOR is the thing that's hard to refute and what's determining the complexity of the problem. So then the right-hand side there, if you can flip one of the negations, it's going to be just like the product of all the negation signs. So that gives you complete control on the k-XOR part. And so that means for that k-XOR part, you're given like an actual worst case k-XOR instance. And all the rest you can refute, but that's not the thing that's like determining the hardness of the refutation anymore. So that seems hard, again, for that reason. This is what I mean, it's not so easy. Because you have to break the current algorithms in a way that looks still doable. Okay. Oh yeah, I guess I didn't say this generalizes all the fully random instances. So it's the same picture, just that random. Okay, so that's actually, that's it for refutation. Okay, we kind of got it. Now we got to talk about planted CSPs, which is what I actually wanted to talk about.
Peter, can I ask a question about refutation before you move on?
Yeah.
You go back to the slide. How does the graph change for non-deterministic algorithms? Like, let's see.
Okay, for non-deterministic algorithms.
FAO business.
Yeah, okay, so this gets even more complicated. Yeah, so as you've all said, there's this FKO thing. Okay. Now I have to distinguish between strong and weak refutation. You're not making my life easy, Rob.
We can also do it later.
So strong refutation just means you want to certify the value is like less than, I don't know, 0.99, let's say. Let's pick a fixed constant. Weak refutation says you want to determine it's just unsatisfiable. Okay. For non-deterministic algorithms, strong refutation, we don't know how to do anything better than this. This is what we know how to do. Okay.
Sorry, say again, strong refutation means?
Certifying the fraction of clauses you can satisfy is, say, at most 0.99. You can actually even go for like what we call ultra strong refutation, which for like 3 sat is determining it's almost 7/8 plus some small thing. So you can get, try to get down to like the mean, which is like the optimal thing.
And we don't know.
For non-deterministic, we don't know anything better than the deterministic algorithms. For strong refutation. For weak refutation, we have these FKO certificates that the trade-off is not so easy to state, but you're able to beat n to the t over 2.
By a lot?
By some polynomial factor, it's between n to the t over 2 and n to the t minus 1 over 2.
So I think the 1.4 for t equals 3.
It's 1. Yeah, it's n to the 1.4 for t equals 3, but the thing is like harder to to write out for larger.
So the saving is a root n for every t.
It's not root n for every t, no.
Like,
It's at most root n. What you do is you basically, again, take the Fourier decomposition of the predicate, use your deterministic strong refutation algorithm to refute all to the at most t minus 1 XOR parts. And then for the t XOR part, you do something different.
What does it mean refute the smaller?
So this is going to be like a system of linear equations. You can argue that the fraction of constraints you can satisfy is basically like half plus or minus a little of 1. So actually any assignment will be not much better than half, but not even much worse either. In terms of like a polynomial you'll write, you'll see some of this later. You're basically saying that like any assignment on this thing has absolute value at most like little o of 1. It's little o of 1 because once you go above n to the t over 2, like really what this is saying is if you're at n to the t over 2 divided by epsilon squared, the bound there is epsilon. So then if you're given like a t minus 1 XOR instance and you're given more than n to the t minus 1 over 2 things, you get like, you can think of that like this, if this is n to the t over 2 and you're trying to refute a t minus 1 XOR, your epsilon is now root n. Or your, I guess epsilon squared is root n. So you get some like little o of 1 there. Okay. And then you get some other way of refuting the top level t XOR instance, and you have to balance that against this little o of 1 factor, and you find like the optimal trade-off, and that gives you the, in the case of 3-sat, n to the 1.4. I guess formally these FKO certificates were initially for only random refutation, and then our work extended it to semi-random and smooth. But they basically, you know, the whole principle is the same. It's once you have the algorithm for semi-random, it's kind of immediate.
What's the certificate in the end?
So the certificate is like the spectral norm of these matrices all the way down, plus like this even cover thing where you're given a collection of violated even covers, and then you can just check those are all unsatisfiable. And then
And which part of that is using the non-determinism that you?
the even covers, because those are hard to find, but they're easy to check. Okay. Enough about refutation. Okay, let's move on to planted. We wanted to talk about planted today, guys. Okay. So what the random planted CSP? Okay, so you're going to sample these things from some distribution. That's a joint distribution where it gives you the instance and some assignment x star, where x star is hidden from you and you're only given phi as the input. And x star is a satisfying assignment to phi. Now your algorithm is supposed to output an assignment, and you want the assignment to be a satisfying assignment with high probability when you're sampling from this distribution. Okay. Sometimes you may even want a stronger guarantee, which is you may want to actually recover x star exactly. That is, find the hidden assignment. You'll see that this is not really possible, actually, even in the fully random case for most predicates. But what will happen is you can at least output some like short list of assignments, of which one of them is guaranteed to be x star exactly. Okay. Okay. And again, we have the same, you know, thing where we want to minimize this runtime clause trade-off. And now I need to tell you what this actual distribution is. And the thing about planted instances is defining this distribution gets like a little bit tricky. It's not so easy. So here's a simple attempt. Okay, you can choose an x star arbitrarily or at random if you want it to be random. It's all fine. And you can then sample each clause by first picking your set of k variables at random, and then sampling literal negations conditioned on x star satisfied. Okay. This is clearly going to give you something which x star satisfies the instance, but there's a pretty big problem here, which is that this instance can be solved in polynomial time when I only give you like n polylog n clauses. Okay. And it's because you planted the x star in some way that was a little bit dumb and makes it very obvious how to identify x star. And here's the algorithm. Okay. For each xi, you count the number of times it appears negated versus the number of times it appears unnegated. You take the majority, and that just determines xi or gives you xi star exactly. And the reason for this is that your distribution over your negations was biased. Okay. If you think about 3-sat, right? There's 8 possible literal negations. But if you want x star to satisfy the clause, now there's only 7. when you picked all 8 uniformly at random, your bias, you know, 3Ys, and they're all independent. It's 3Ys independent, everything's great. Now you pick one of the 7 possible things, and suddenly even the mean of each individual guy is biased in some direction. In fact, the direction it's biased towards is xi star, and this makes it very easy. So we're going to just generalize this a little bit and define something called a planting distribution. Okay, so the planting distribution is just a distribution over satisfying assignments to the predicate. And now we can define the so-called distribution complexity of this thing, which is the size of its smallest non-zero Fourier coefficient, or equivalently, you know, it's going to be R if the thing is R-1 uniform and not R uniform. Okay. If your predicate is non-trivial, you're not going to be able to put a k-wise uniform distribution. So the distribution complexity is always at most k. It's also defined at least to be at least 1, though I guess the formulas I'm going to write will not actually make sense if the distribution complexity is 1, so always think of it as at least 2. Okay. That's because at some point you're going to write this thing divided by 2, and I don't want to write like max of 1 comma a thing divided by 2 like on every slide. Okay, so there are non-trivial planting distributions. There's a famous one called the try-sum and one for 5-sat, where you sample basically random signs such that B1 plus B2 plus B3 plus B4 times B5, this is not a typo, this is meant to be multiplication, is equal to 1. You can check that this is pairwise independent and not 3-wise independent. Okay, so its distribution complexity is 3.
So what happens if rather than sampling this stupid bias thing which is easy to detect, you simply take a random instance, a random flipping of the negation, and then throw away all the clauses that are not satisfied by X. No?
That's the same thing.
That's
the same thing,
right? Yeah, okay, that's what I want.
You're just conditioning the clauses on. So that's the same thing. Yeah. Okay, so this is the distribution complexity. As you can imagine, you know, this is going to matter. Okay, so now we're going to plant k-CSPs with distribution complexity R, and you can notice I put R everywhere suddenly, and that's because the algorithm that comes from this work of Feldman's, Perkins, and Pampala gets this polynomial time case, which needs n to the R over 2 constraints when you're planting with distribution complexity R. Again, if you plant with distribution complexity 1, you need n constraints. So like this is really, you know, max of 1 and R over 2, but
so for 3-sat, it will still be 3.
For 3-sat, okay, the only way to plant a 3-sat instance with distribution complexity 3 is to plant it like a 3 XOR instance. The problem here is the way I've defined it is I'm making X star satisfy the instance. So this is linear and this is easy. I could make it so X star only needs to satisfy 1 minus epsilon fraction of the instances, and then you can plant like this and you get some interesting problems again. But formally, if you want your thing to satisfy, like X star to satisfy the whole instance, there's actually no non-trivial way to plant for 3-sat or even 4-sat. And that try-sum and predicate is actually the first one you get at 5-sat. Good. Okay, so our result, which is somewhat recent with Arpon, Andrew, and Tim, is we basically just complete this curve. Okay, we get the sub-exponential time region.
I'm confused by the graphics. What's the dashed line and what's the orange line?
So the orange line is our algorithm. Oh yeah, I didn't mention this. The dashed line is the lower bound, which is formally for refutation, so it actually doesn't apply anymore. On the other hand, depending on how you feel about it, some people like to view refutation lower bounds as lower bounds for the planted problem as well.
So what do you mean depending on how you feel? Like it's not necessarily true.
It's not necessarily true. No, like if you plant in a really dumb way, like the lower bound goes out the window. Like the point is if you
I see, but for like the reasonable way that
if you plant with distribution complexity R, you can kind of reduce it to the
okay.
and it looks like well, no, because okay, I'm gonna give you an algorithm that where this lower bound like makes sense, but like you'll see why this doesn't make any sense anymore. Okay, here's my algorithm. I run SOS, I compute its like optimal thing. And here's how I round it. I throw the pseudo expectation to the garbage and I run my algorithm that solves 3-set in polynomial time because P equals NP, and I solve my instance. Okay, that does not violate any of the lower bounds here. And this could exist. So that's why this sort of thing like starts breaking down once you go to planted instances.
I didn't, sorry, say it again.
The problem is, how do you define what it means for SOS to like fail to recover the planted assignment? Because the way you usually do this is you say that like, for refutation, you just say the pseudo expectations value is what we declare SOS's value to be. And if that is 1, we say it failed to refute. But for planted distributions, you need the pseudo expectation and you need a rounding procedure. And the rounding procedure can be this dumb thing where you discard the pseudo expectation and solve the instance with a totally different algorithm. And this is a valid rounding, like technically. So I don't know. I mean, formally, you can show things like if the pseudo expectation is value 1, you know, there's no generic rounding algorithm for the pseudo expectation that will just only given the fact that it's value 1, give you a good assignment and things like this. That actually just follows from the refutation lower bounds kind of immediately. But formally, it doesn't like rule out some really clever rounding algorithm.
I mean, but for this really clever rounding algorithm, you need to look at the instance again. You can't.
Yeah.
Rely on the.
Yeah. So if you're saying you're like only allowed to look at the pseudo expectation now, then you can do stuff. But like, yeah.
I mean, your objection is for even older SOS lower bounds for any CSP, right?
Yeah, yeah. It's like the lower bounds are really specifically for refutation. You can try to make some analogy to the planted case and say like you believe it still works, but like formally it's not what the lower bound is showing. So you should always be careful. It's a warning sign. Okay, so I want to talk a bit about how how these algorithms actually work. And the way they work is they reduce to some problem called sparse learning parity with noise, or I guess X or KX or RX or in this case. I'm setting my sparsity to be R. These are just a very simple problem. Given n variables, I get equations. I'm writing the equations as like this, where I have for each hyper edge C, which is my equations, I just take the sum of the variables there. And then I have some right-hand side B sub C and 0, 1. And these are sampled by first choosing your planted assignment arbitrarily, and then sample each equation by choosing a random hyperedge and setting the right-hand side to agree with the planted assignment with probability half plus epsilon. Okay.
So how should I think of R?
R is like a constant. So R is going to be between like 1 and k. In fact, you'll see this in like just a second. So the goal here is we would like to recover X star exactly. Okay, meaning if R is odd, you can do this. If R is even, you can't, because there could be like a global flip of the bits because it's even, so that would like cancel out in every equation. But up to that, you can recover X star exactly. Okay, and once you have an algorithm for this sort of thing, let me now explain how you get to this from a k-CSP with planting distribution Q, distribution complexity R. It's very simple. You first take the non-zero Fourier coefficient, which already should raise some alarm bells because you don't know what Q is. So you actually don't know what this is. The way you do this is you really just try all of them. And like the one that is there will work. And then you will get, like, so this will give you a list of candidate assignments. One of them will be X star, and X star will satisfy the instance. So you'll win. Okay. So let's say you have a clause, it's got variables I1 through IK, and the negation signs are B1 through BK on it. Well, you have some set S, it's a subset of K. And what you do is you just make the equation that kind of plucks out the variables from S and the signs from S. Okay, so you just take your equation, it's like sum of J and S of X of IJ. And the right-hand side takes all the corresponding B's that you had, the signs, and puts them there. And a pretty simple calculation here is that this actually agrees with X star with probably like half plus up to a normalization factor, the Fourier coefficient. Okay.
Sorry, what is B1, for example?
So if B1 is 1, then like
Where
X.
did I get B1 from?
So you have the CSP, which has the literals and their negations, right? So B1 is 1 if XI1 is negated in the clause, and otherwise it's 0.
I start with the CSP, not this XOR thing.
Not this XOR, and I reduce it to the XOR thing by like
I see.
converting every clause into one of these XOR
This
things.
is your reduction.
This is the reduction. There's like one minor thing, which is that this could be negative, in which case this is negative. So actually X, like the noise here is like more than half, but you can just guess the sign of this and like flip the right-hand side. So it's not a big deal. And you just do this, and this gives you like a list of candidate assignments. One of them is X star when you picked the right coefficient and you win. Okay. And yeah, so this says that if you can solve this problem with like n to the r over 2 constraints, then you can solve the k-CSP with planting distribution Q with distribution complexity 1.
Sorry. Oh, you're saying this agrees with X star. It should agree with any satisfying sign.
This?
Yeah. Like,
No, it's X star specifically. So
okay, I mean, suppose I find some satisfying assignment to this set of equations. Or
Yeah.
like
that might not work.
trivially,
That will not work. No. The fact here is that I can actually recover X star exactly. For the learning parity, the sparse LPN instance.
Okay.
So you recover X star exactly, now you don't even need to worry about the original constraints, because one of them is like X star satisfies it, and you've got X star.
So you're saying that you get this set of equations and you can recover X star exactly, not necessarily, maximally satisfying.
No, you get X star, but X star is a maximally satisfying thing. Yeah. Okay, so this is like the whole reduction.
So epsilon is like 2 to the k minus 1 times the Fourier coefficient?
Yeah.
Okay.
Yeah, you could worry that like some of these things have like, there's a non-zero Fourier coefficient that's like really small. Prior works actually just assumed this thing was like considered constant relative to n. You can consider the case where it's not constant. And then you modify your definition of distribution complexity slightly to like care about the magnitude of this thing.
I think initially you assume Q is a Boolean predicate, so you have a lower bound.
Q is a distribution.
Q is a distribution over Boolean values also.
So
Doesn't it still have like a lower bound on the smallest?
oh yeah, actually, no,
It
I
only
think,
takes key variables. so-
yeah, I think you're right. I think it's like 2 to the minus 4k or something. I think there is some lower bound. Yeah, you're right. Yeah, okay, no, never mind. Yeah, you're right. I forgot.
So you know this Q in advance?
You do not know, but you just guess which coefficient to look at. You don't need to know the magnitude of the coefficient to run the algorithm. You just need to know which coefficient to look at. If I tell you the set S, you can just do the transformation. And you can do this transformation for any possible S that you want.
So you just use some uniform bound on.
You just need there to exist the coefficient. And
I
then,
just mean you don't need to know it because you can just run it at some like universal.
yeah, there's like a universal algorithm that doesn't depend on epsilon.
And it enumerates 2 to the k.
So the universal algorithm is for the LPN instance, the sparse LPN instance.
I think he's saying like there's only exponential.
Yeah, there's only 2 to the k
possible
possible choices of the coefficient,
Yeah.
and k is like 5.
Okay.
So that's, yeah, so that's not a big
Fixed
deal.
constant.
Fixed constant. Actually, you lose another factor of 2 because you have to guess the sign of this thing. But that's also fine. Okay. So I kind of told you about planted CSPs, but I only told you about the random case. And I want to tell you about the semi-random case, and you'll see that the wheels are going to come off, so to speak. So here's the random planted thing. I said I want to make it semi-random. What do? Okay, I just make my hypergraph worst case. So I cross out random everywhere, and the main thing that changed is C is arbitrary. The first thing I want to point out is that we're not going to be able to find an X that satisfies the instance anymore. This is just not going to happen. We're going to only be able to satisfy 1 minus the low of 1 fraction of the equations, and I can more or less prove this is necessary if you're willing to assume like kind of that we got the optimal algorithm in the random case already. Okay.
What? You're saying like.
If you're willing to assume that our algorithm for the random case is like optimal already, then you can prove this is required. It's like a modified version of, if you know about like Feige's three-set hypothesis.
Yeah.
Yeah, it's like a modified version of that that's for refutation. You just have to make it the predictive version.
You are saying you're justifying why you cannot find the solution X.
You're not going to be able to, okay, first of all, you're not going to be able to find X star exactly. You're not even going to be able to satisfy all the equations. I'm going to show you a proof of this on the next slide as to why this happens.
I mean, if you just choose arbitrarily to like omit some variables.
Yeah, that already, you're coming up with a proof. This is not very hard to show. I guess the other second point is the distribution complexity turns out to be just like totally wrong and doesn't mean anything anymore. Okay, so this is what I mean by the wheels are coming off. So the problem is we cannot recover X star exactly. For example, as your Tom points out, you could have your variables, you split them into 2 halves. And what you do is you just like literally put all the clauses only on half of the variables and you put literally nothing on the other half. Okay, the game's up. Like I have literally no information about X star here. I clearly just can't do anything. But the example that makes this slightly worse here to show that I cannot not satisfy all the equations is that what I do is I put most of my clauses here and a very small number of clauses here. And what happens is if I want to satisfy all the constraints now, is I have to basically solve 2 different CSPs, right? There's the CSP over here on this chunk, and there's the other CSP on this chunk. And the problem is I can make this density like really tiny, okay? So I can maybe put like literally n clauses here, or like order n clauses here. And now you're in the regime where if you wanted to satisfy all the constraints, you need to satisfy a random CSP on order n clauses. And actually like the picture I had before says that kind of expect this to take exponential time. And on the other hand, you could have something very easy here that you can do. So what this means is you basically just have to give up on this other half of the constraint. There's no way around this. Good. So this is the problem with exact solutions. There's another problem with distribution complexity. Here's the problem. Here's my predicate. Basically is like a real predicate with an and of one extra variable, okay? And you can observe that what I've done by adding this and thing is I made the distribution complexity be 1. Okay, because this guy's Fourier coefficient is biased. Okay. So problem here is that to satisfy a predicate here, I need to satisfy like both the real predicate here as well as this like fake little thing over here. And what I can do is I can again split my variables in half and make all the real stuff come from one half and the fake thing come from the other half. Okay, and the thing is the distribution complexity thing tells you that with order n constraints, what you can do is you recover X star exactly on the half that you don't care about. That's not like the real part. And the problem is now you don't get anything about this part here because assuming this is like a k-1 array CSP with distribution complexity k-1, what we said is you need like n to the k-1 over 2 constraints to even learn anything over here. So you're in trouble. Right, so the distribution complexity on the F part could be k-1 and it's over, right? So this is not a counterexample for random. And the reason this doesn't work for random instances is that the random instance will draw like this xk part from like the whole thing. So you'll learn information about all of x star from this part, and that will actually just give you x star and you win. But in the semi-random case, you can kind of make it so it targets a specific part of x star that then doesn't actually give you really any information about the part that determines the satisfiability, and you lose.
But the weird thing is that this problem didn't show up when you did the semi-random
For refutation?
refutation.
Yeah, this is the problem. This is why I said planted. This is why I said refutation first. The planted thing gets much more complicated.
Kind of now looking at this, I would expect that problem to already show up there, right? So strange.
Uh,
I guess you refute where the place where it's hard, and it's,
yeah.
maybe that also explains why you don't get strong refutation so easily.
You do get strong refutation easily in the semi-random case. It's just that like, if you can't recover X star, it doesn't matter. Right, like refutate, it's just like a totally different thing. It's,
Yeah, it's somehow, yeah, this seems more like getting at the actual problem.
I mean, I don't like disagree with you. I think the planted case is harder. Like, okay, but I'm gonna tell you, let me just, two more things, okay? First thing is you can kind of plant like this for k-stats. This is not like just like a random, this is not like a crazy predicate to consider. These are like real problems. Okay, so the thing about semi-random is that the only thing we know how to do is actually the polynomial time case, okay? So this is kind of going back to what you're saying here, is that the planted case is, I think, just harder than the
More
refutation.
interesting.
More interesting, yes. I mean, it is more interesting. There's some additional challenges here that we managed to get around to the polynomial time case, and you'll kind of see why in a bit. But in the sub-exponential time regime, we don't know what to do. So we've generalized the polynomial time algorithm, but here we don't know. Okay.
And you said you also don't know the correct parameter?
I mean, we think the whole thing is achievable, like the same curve for the semi-random case.
No, but for which parameter? For K.
For K, yeah.
Maybe you need like a regularity lemma to get it to dense places and to do it differently for different density.
We have tried these things.
You've tried this.
Yeah. I mean, I guess I can say we do have some ideas that seem like they might actually work, but like the calculations are going to take some time. But yeah, I mean, it could still break and stuff, so. It looks like a different beast. You'll see when I start doing things on the board, there's like part where you can do with refutation, and then like there's part that like really looks different. It's sort of the difference between like bounding the spectral norm of a matrix in absolute value versus like comparing it to a different matrix and wanting one to be smaller than the other. So that like that other statement is like, you know, if one matrix has a lot of like weird eigenvalues at different scales, and you kind of need to match the two together. Whereas in the other case, you just need to bound so that the kind of the top one is the only thing that matters. Okay. Yeah, so the final thing I want to say is about this reduction to sparse LPN. You know, this is the thing that we had for random. To try to make it work for semi-random, the answer is you just lose. You can't recover X star exactly anymore. So what Tom was asking earlier about like, how do you know you're satisfying the original constraints? Before we knew because we got X star. Now we don't get X star, right? You could find something that satisfies this thing, like maybe like half plus epsilon fraction of the constraints or something like this. But why should this be satisfying the original constraints, right? You don't know that. Because you're not getting X star out. And this is, I mean, as we pointed out, you know, you can't recover X star exactly anymore. So things aren't really working. It turns out you can make the reduction work, but it requires like some new ideas. And also you need a much stronger goal with this. So I won't actually end up showing you the reduction, but I will at some point get to the goal that you need that will make the reduction work. Okay, so yeah, that's it for planted CSPs. I've been talking for a little over an hour now. I guess these are the two results. You know, we had the semi-random case, polynomial time, random case, the full trade-off. Yeah, I think this is a good time. Take our little break. Okay, so for the remaining part of the talk, I want to give you a vaguely complete proof of our algorithm for semi-random sparse LPN, at least for the case where k is even, where it will be simpler. So I've written some definitions here, but this is kind of the thing I've already told you. The main thing is I've switched from 0, 1 to ±1, which is what we're going to now just work with. Okay, so we start with a k-uniform hypergraph. It has about n to the k over 2 hyperedges, which are the constraints. We have a planted assignment x star, and we set the right-hand sides of the equations b sub c to agree with x star, meaning it's a product of I and c. X star sub I with probability half plus epsilon over 2, and otherwise it's the negation of this with probability half minus epsilon over 2. And I should say that the constraints look like this. They're like product of I and C, X of I should be equal to B sub C, and this is for all hyperedges C. Okay. So the next thing is I've defined this polynomial psi of X. This is the average over the constraints of the product of the left-hand side with the right-hand sides of the equations. Okay, so if the equation is satisfied, this thing is going to be +1, and if it's unsatisfied, it's -1. So this just computes the fraction of equations you satisfy minus the fraction that are unsatisfied. Okay, the reason for this is that this is going to be like nice and mean 0, meaning, okay, if I define the value to be the maximum of this polynomial over assignments X, then wanting an assignment of good value or something beating half means I want psi of X to be like epsilon. That means I'm satisfying half plus epsilon over 2 fraction of the constraints.
The same epsilon is.
It's the same epsilon because they're going to get a half plus epsilon over 2 minus half minus epsilon over 2. You get 2 epsilon over 2s, which combine to be an epsilon. Okay. So that's our goal. We're given this set of constraints and we want to find an assignment satisfying about the same fraction of constraints as X star. As I've already said, this is not going to be sufficient to get the general algorithm for k-CSPs, but eventually we'll work towards getting a better goal here and then things will work out. Okay, let me start with the following warm-up, which will be the case of k equals 2. Okay. So rather than looking at a general k-uniform hypergraph, meaning the hyperedges have size k, now we'll just have size 2. Okay, so this means what are our equations? Our equations look like, we got like xi xj equals some bij for ij in my set of edges. So here's the algorithm. I'm going to give you the entire algorithm. I'm going to write it on the board. Okay. So first we set A in R to the n by n. It's going to be the signed adjacency matrix of this graph. Okay. So that just means Aij is one of two things. It's Bij or 0. And this is if there is an edge. And if there is no edge. Okay. The next thing I want to do is compute the so-called basic semi-definite program. Solve the basic semi-definite program. Okay, which is to say what you want to do is you find x and r to the n by n, which maximizes the inner product of x with a, which is a little bit of strange notation. This is just sum over the entry. So it's like think of the matrices as big vectors and take the entry-wise product, or entry-wise inner product. Okay. So you want to maximize this, subject to two things. The first is that you want the diagonal of x to be all 1, and you want x to be positive semi-definite. Okay, so if you haven't seen this before, this is going to look a bit mysterious. Let me interpret this for you a little bit. I do want to point out that x equals to xx transpose for x and plus minus 1 to the n is feasible, meaning at the very least it's satisfying all these constraints. Okay, and you can just check this. If x is in plus minus 1 to the n, this matrix has diagonal all 1s because its diagonal is xi squared, which are 1s. It's positive semi-definite because if I take any quadratic form on this, I just get like its inner product with x squared, which is non-negative. Also, this maximum thing, xx transpose of A, is, you stare at it, it's just this thing. And by the way I set it up, this is psi of x. Or I guess I have to multiply by m because I didn't normalize. Maybe I should normalize. Let me normalize. Okay. So now it's just psi of x. Okay. So this is some sort of relaxation. We're not optimizing now over assignments, which is what we wanted to do. We're optimizing over some other thing. And the point is this thing has like a separation oracle. You can solve it with the ellipsoid algorithm, polynomial time, or at least get some x that is close to like a maximizer here. Okay. So the next thing we're going to do is, given an SDP solution, I need to tell you how to round it. And we're going to round it in the sort of classical way. Something called Gaussian rounding. This is the same rounding as using the Gomez-Williamson rounding for Mexico, okay? So all you do is you sample a Gaussian in the normal distribution. Mean zero covariance matrix is X, which is your SDP solution, okay? This is valid because this is PSD. Okay. You set xi to be the sign of GI, and that's it. So far, this is pretty straightforward. I now want to argue that X satisfies psi of X leaves epsilon minus the low of 1 with I. Okay. Okay, so let me prove this claim. If I prove this claim, we already are going to be hitting this goal over here already, at least for k equals 2. Okay. So here's the proof. I define a subset of my edges to be the following set. I'm going to view my noise procedure as being a little bit different. Okay. Instead of taking all the edges and either making it agree with X star with some probability or disagree with the other probability, I'm going to think of it as I first pick edges where I make them agree. And on all the other edges, I put random signs. Okay. So E prime are the random signs. So for IJ and E prime, Bij is uniform from plus minus 1. And IJ in E minus E prime, Bij is the correct thing. It's X star I, X star j.
So this side is E minus E prime, is that?
Exactly. Yes. So size of E prime is about 1 minus epsilon the size of E. Size of E minus E prime is about epsilon. Right. So your whole advantage over a random assignment has to come from these edges.
Can you explain once more why each clause turned into a product instead of a bunch of cores?
Oh, I'm working with linear equations.
Oh, okay.
Yeah. So I'm taking a sum, but I'm writing a plus minus 1, so it's a product now.
Okay.
I think of it as like minus 1 to the thing over F2.
Okay.
Yeah. Okay. So the next thing I can do, I can take my polynomial psi, which I'm going to think of it as like psi sub E for all the edges. And I write it as psi E prime plus psi of E minus E prime. Except I need to add some normalization factors because this guy was like normalized by dividing by the total number of edges. This guy has a smaller number of edges. So the rescaling is just by these terms. And as we pointed out, this rescaling term here is 1 minus epsilon, and this rescaling term is epsilon. Okay. We also know that the SDP solution satisfies two things. The first is that its inner product with the whole thing, so you divide normalized appropriately, is at least epsilon minus the low. And that's because it's always at least as good as X star, because this is a relaxation and X star is a feasible solution, right? It also satisfies that on this E prime part with the edges are randomized, that this thing is at most little o of 1. And this is by refutation. This is exactly what the refutation guarantee says. The refutation guarantee that I'm not going to prove for you just says that if I compute this maximum where all the right-hand sides are actually uniformly random plus minus ones, I only get a little o of 1 here. I mean, technically it's a constant, but if I like increase my polylog factor, it's like the o of 1. Okay. The point is, now that I have these two things, I can check that, well, this says that if I look at the whole instance, I have like an epsilon here. If I look at this part, I have a little o of 1. So that means the epsilon has to come from here. Now, this thing actually has an epsilon in front of it. So what this really says is that like X with a E minus E prime over size of E minus E prime is at least 1 minus a little o of 1. Okay, now if you know the analysis for Gaussian rounding, which I'm not assuming you know, I'm just going to state the main result here is that if you have a 1 minus the little of 1, this implies that the X that you get out has XX transpose, like inner product with this thing, at least 1 minus the square root of that little o of 1. Okay, but it's a square root of a little o of 1, it's still little o of 1. And the other thing you can put together is that for the refutation thing, this also holds for X. Actually, in fact, this is not just true, it's like it's true in absolute value and it's true for all solutions. So if I combine this with the bound here that I also get on the assignment X that I get out of my rounding, I can just check that, like, you know, its value here is small, its value here is large. So its total value is this minus whatever that is. And this thing was tiny, so it doesn't do anything. And I'm left with my epsilon, or I guess I have 1 minus the little 1 times the epsilon. Okay, so that finishes that.
Wait, where did the E prime come from? I thought you were gonna tell us where the E prime came from.
No, you've noticed something bad about this, which is that the E prime subset is actually arbitrary in this entire proof. I do not need it to be random.
Okay.
This is a real problem. Okay, it's a real problem because I'm going to show you in a second why this doesn't work for k equals 4.
Okay.
Yeah.
So
So this does work for k equals 2, but k equals 2 is
E
like
prime at all.
any E prime at all. Like if you take your edges and you make half of them, or not half of them, some set E prime of size 1 minus epsilon being random and the rest agreeing, this actually works, and it doesn't matter where you choose the E prime locations to be.
Yeah, that does
Sounds like I did something wrong. Yeah.
So why the first inequality is only like epsilon minus little 1? Even this X star providing at least epsilon?
Well, I mean, the way I set it up is it's like epsilon and expectation. You might like fudge it a little bit, yeah.
And the second absolute value being at most little 1 is like unimod over all X?
This is actually by like computing the spectral norm of this random matrix, yeah. This is the refutation case.
Okay, one nice property that you already use and might be commenting on is that the Gaussian rounding is completely oblivious. It doesn't care what the objective is. That's why you could just analyze it on.
Yes, exactly. Yeah. Yeah, because when you do the Gaussian rounding, you get an X and you can like look at what X looks like here and what X looks like here, and it doesn't matter. Good. Okay, so now I want to get away from this because this is not going to work. So the real case, that was just the warm-up. So the warm-up is to tell you that k equals 2, kind of anything works. And for k equals 4 is where you see if you went wrong for k equals 2 or not. Okay, so this approach is not enough. And let's see why. So here's our strategy. So our overall strategy is going to be doing the following strategy. So the first thing we want to do is we're going to reduce k equals 4 to k equals 2. Okay, this is something that Oliver mentioned yesterday a bit. So let me just tell you this reduction. Okay, let's say I have equations that look like this. Let's say I have a 4 XOR. I'm going to write the 4 XOR variables as the y, so that the 2 XOR will be still 8x. Okay. So I have an equation like this. It's my instance phi. K equals 4. The number of variables is n. The number of equations is n to the k over 2, which is n squared. And we have like our hidden y star. Yeah. So transformation is pretty easy. All I do is I make like a new meta variable for per pair of the original variables. So I have like xij, xu, v, right? And then this is equal to some b sub ij. You are getting out of space, but it doesn't really matter. Okay, so this is my new instance psi. I have k equals 2. Number of variables is n squared. Number of equations is also n squared. Notice now they're matching. So there's like a polylog here, so it's making the average degree be polylog now. And I have a hidden assignment, which is x star, which is y star kind of tensor 2. Okay.
Wait, so are those new variables ordered?
They don't have to be.
So each ij you read from the left-hand side will give rise to like or choose 2 different.
Yeah, but you can pick an arbitrary way to do it. And that only loses you like a constant factor on the number of edges, so it doesn't matter.
It changes the underlying semi-random model, because there are correlation between those two.
Sure. So you could
you could use like ij grouped together and uv grouped together, and then you can group iu and jv.
So you could pick an arbitrary one of those and just keep one.
I say you just keep one.
You can do the analysis by keeping all of them. Like it doesn't matter. Basically, yeah. It doesn't help, it doesn't hurt, it's just a constant. Yeah, it's basically like trying to determine like the exact constant in front of this like n squared here, which, yeah. Okay, so the second thing you're gonna do is you're gonna solve this 2 XOR psi, right? So this is going to give us an x such that psi of x is like epsilon minus the log of 1. Okay, and now you can see what the problem is. I need to recover a y. I'm given x. X may be not equal to like any y tensor 2. And now I don't know what to do. Okay. And this is sort of the problem here. Like the x you're going to find here is not going to look like this. It's not going to work. Okay. So nonetheless, we're going to make the strategy work anyways, but we're going to do it by doing the 2 XOR case kind of the right way, or in at least a better way than this, in a way that will actually make this work. And the key idea is that we solve, when we do this thing, we find x star. So like that is we output x is equal to x star at the end of it. When we solve this instance, we don't just get some good assignment x, we actually got x star. Now x star actually has this tensor structure. It's very easy to just read off y star given x star. At the very least up to like this global sign, which doesn't matter. Okay. So the real thing we need to understand now is what conditions will make it so that when we solve the 2 XOR instance, we will quite literally just get out the planted assignment. Yeah.
You try to like pick the edges, E primes that are disjoint or something. Like not correlated so much as an arbitrary segment.
Yeah, I mean, yeah, you'll see. It's like you want it to be. Well, you'll see what the actual condition turns out to be in a bit. Yeah. I mean, that's like good intuition, yeah. Okay, so we want to understand conditions on this graph G that we start with, so that with high probability, when we like solve this basic SDP, that the output we get is actually just literally X star.
You're fine, though.
Well, you don't know how much there is to go. Okay, so I'm now going to. Don't like the space. Okay, let's go over.
When you said the graph G, did you mean
Like E. Yeah, just.
the hypergraph?
Well, so you start with a hypergraph and you converted it to a graph over there.
So you're now looking at the graph.
I'm only gonna look at
After
2
you
XOR.
squared up,
Yeah. I'm only gonna look at 2 XOR. Notice that the hypergraph semirandom, the graph you get is also semirandom, so this is not like a problem. Also, if the graph is random, the other graph you get kind of is random also. So it's like, kind of in both cases, it's the same.
So sorry, just to repeat what you said, if you promise that you found the actual planted solution,
X star, yeah.
then it will happen to be some white under white.
Yeah, you can just literally like read off Y star from that. Like the only information you're losing there is like the global sign on X star, but if K is even, we've already lost that anyways, so it's not like.
It's only a factor of 2.
No, it's like you can't even identify this. It's not a factor of 2. It's like information theoretically like X star and minus X star, this is the planted or sign. Okay, so let's now. Don't get this anymore here. When I write bigger, I run out of space faster.
Is that a theorem?
When I write.
Size versus.
Have you considered using less vertical
Mm,
space?
What?
Have you considered using less vertical space?
No.
There's like a bunch of space.
Yeah, like, I don't know, that's fine. Okay, so.
Yeah, I was gonna say, definitely there's something catalytic you could do.
Guys, you're deteriorating, come on.
Okay, so I'm gonna switch my notation slightly. I don't want to use E and E prime anymore because actually I'm gonna just totally go away from that model again. I'm gonna go back to the original model where I'm gonna have G, I'm just gonna call this be like all the edges. And I'm gonna let H subset of G be the corrupted ones. So this means that if Ij is an H, Bij is minus X star I, X star J. And if Ij is in B minus H, Bij is that thing, but no minus sign. Okay, so this is when it's correct, this is when it's incorrect. What I first want to do is tell you a condition under which, at the very least, you could find X star exactly using brute force. Okay, because at some level, if I give you the system of equations, it may be that like I give you an actual system of equations where you can't even identify X star, even if I give you exponential at time. Okay, because I'm asking you for something much stronger than just trying to find a good assignment. So let me write down the condition. Okay, so let's suppose that when I take so these are the unnormalized Laplacian of G and the unnormalized Laplacian of H. Like if LG minus 2LH, I look at its quadratic form on X where I want this to be strictly greater than 0 for all X and plus minus 1 to the n. So all assignments except for the all ones. Okay.
So being unnormalized means that LH is like only epsilon fraction of the norm of LG?
You would hope. Yes, you would
What
like.
do you do? How much
Or
do you?
LH has half minus, so this thing has like half times 1 minus epsilon of the edges. So you would like it to be like half 1 minus epsilon of the norm of
Oh,
those.
sorry, you correct almost half of the edges.
So let's suppose this condition does hold. Then X star is the unique maximizer of the instance. That is, if I just compute all assignments, take the best one, it is actually X star. The proof here. Uh-oh, what did I break? So the proof here is not actually terribly complicated. I just have to sort of go through the motions. I write my polynomial psi of x. It's the average over the constraints, the sum of the edges, xi, xj, bij. And now I just need to group this properly. So basically, if I have something in G, well, I'll write it like this. Minus you probably can't see this here.
Yes, and the condition you could also take minus one again, because you can vary.
Yeah, thank you. Let's see.
Do you really want to just orthogonal to all ones?
Yeah, yeah, sorry. It should be it should be orthogonal to all ones. Yeah. Good. Okay, I don't know if you can see this very well, but what this is it's you sum over the edges in G, take xi, xj, and then replace bij with x star I, x star j. But I'm left-handed. Okay, and then on the h you take a -2, and that's because if my edge is in G and not in H, then I get a plus x star I, x star j. That's exactly what bij is. And if I'm in H, I get a plus and then a minus of 2, so I get a minus. Now, all I just need to do is let Z be this vector where it's like X, but like shifted by X star. And I can write this whole thing as Z transpose the adjacency matrix of G minus 2 the adjacency matrix of H. These are unsigned adjacency matrices. There's no signs in it. Okay, the other thing that I now need to tell you with the Laplacians, I guess I didn't formally say it, but these unnormalized Laplacians are exactly just like the diagonal degree matrix of the graph minus its adjacency matrix. Okay, so I can just replace everything like this. I get 1 over m d transpose dg minus 2 dh z minus the LG minus 2 LH, and we are close to done. So if you look at this, these are diagonal matrices. Okay, so I just look at this, I'm actually counting the number of edges in G. This is counting 2 times the number of edges in H because this thing's diagonal is 1. So this term here is size of G minus 2 size of H divided by m, which I want to point out is exactly psi of x star. Because x star satisfies everything in G minus H and violates everything in G in H. So this term here is actually just psi of x star. And that means I've subtracted off some quadratic form on this matrix. And what I've claimed here is the quadratic form is always greater than 0 unless Z here is all 1s or all -1s, which means that either Z, so if Z is all 1s, that means either Xi is literally equal to X star I or globally the negation, or else I get like minus something here and it's not the maximum. Right. So I've just rephrased everything in terms of like the deviation from psi of X star, and I said the deviation must be negative unless you are literally X star. Okay, so I've proven my claim. So the final piece that I need. You anymore? So the final claim that I need. So this doesn't give us an algorithm, right? This is just saying at least information. Theoretically, I can brute force try all assignments, and at the very least, I am not doomed. Like if this is not possible, you clearly cannot do this with an efficient algorithm. Right.
You need to rely on the randomness in H.
You need to rely on the randomness of H to argue that this will actually happen. Yes. So I am now going to give you a condition that will allow for an algorithm, and then I'll explain why that will hold. Or actually why it won't hold, and then how to make it work. But okay. So the final claim for this thing is this matrix is positive definite, which maybe is a little fishy because these matrices actually have this all ones vector in their kernel, but orthogonal to that trivial thing in the kernel, I want this to be positive definite. If this is true, then this SDP solution, literally when I solve this thing, will have X equals X star transpose. As in, I literally just get X star out and I win. Okay. So I can now explain this by just going over to this proof and starting to mark things, okay? So you can just kind of go through this whole proof where you replace like quadratic forms here with like kind of the inner product of Z with like AG minus 2AH, where Z is now a matrix where Zij is like my SDP solution shifted by X. Okay. I can go through the whole thing. Down here, I get inner product of Z with DG minus 2DH. Notice that Z has diagonals all one because X did. And when I shift it by this, it preserves this fact. Okay. And because this is a diagonal matrix, when I take this inner product, the only thing that matters here is the diagonal of Z. And I get actually, again, the same psi of X star coming. Right.
Why are the diagonals of Z all ones after you shift?
So the diagonal of X is all ones.
Yeah.
The diagonal here is XII.
What's written there actually? I can't see.
Oh, okay.
It's Xij and then it's a plus or a minus?
It's got it. Zij is equal to Xij X star I X star J. So the diagonal is shifting actually just by plus one. Right? Yeah. This last term over here just becomes Z LG minus 2LH. Now, Z is a PSD matrix because X was, right? Essentially, the shift by this thing just sort of says quadratic forms on X correspond to quadratic forms on Z, but then you take like entry-wise product with X star. Okay. So because this is PSD, you can write it as like the sum of rank 1 terms, like lambda I, vi transpose, and this thing is greater than 0. Okay. So if Z is not 1 transpose, one of these terms is like greater than 0, and this thing, also its quadratic form on this guy here will be greater than 0. So you get a plus, and actually the fact this is greater than 0, and this is greater than 0 means that you're kind of always getting plus terms accumulating. So this means that the maximizer is just X star, or Z, which is all ones, which equivalently says X equals X star transpose. All right.
So the definition of that being PSD is for other PSD except for 1 transpose.
Well, 1 transpose is PSD also. Like
No, it's saying all quadratic forms orthogonal to all ones are strictly positive.
Yes, this is orthogonal. I should have written this, sorry. Yeah, it's orthogonal to the all ones. Okay, because the all ones is in the kernel of this, it's 0.
Oh, yes.
Yeah.
Maybe it's an annoying question, but
yeah,
when you solve a semi-definite program, you don't really get the maximum, right? You only get something close.
Yeah, but you get something entry-wise close.
Oh, so you're just kind of rounding.
Yeah, so you get something that's like the value on like a thing is like 1 minus like 2 to the minus like poly n. Yeah, so it's all good.
So your function is SDP.
Exponential.
Yeah, 2 to the minus. The poly n isn't the exponent.
So this relaxation is not a relaxation. It gives you a rank one solution.
Do a rank 1 solution. Well, it is saying that you can efficiently find. I
No,
think.
clearly,
Yeah.
but it doesn't use the extra dimension.
No.
Vertical.
So the final thing to finish the proof is to understand when this actually happens. So when is LG minus 2LH equals 0 when H G is chosen like all of like half my sense 1 over 2 IID for all edges, right? So essentially this is like a kind of spectral sparsification statement. Okay, so people have studied questions of the form, you know, when I take some subset of H of G chosen from some particular distribution, or maybe I just want to find a set H. I want this to be like, you know, bounded by like half LG and then be bounded like half minus some other thing in LG, kind of sandwiched in between the two, where this, I'm writing like matrix B less than A if A minus B is greater, like positive definite. Okay, so these are statements like people have looked at in the past. There are some pretty cool things where you can always like take any graph and find like a spectral sparsifier with like a linear number of edges and so on, or n or polylog n.
Yeah, but there you need weights.
But there you need weights, as Avi says. Here we are not allowed weights, we need uniform sampling. And as you can imagine, here's the real, this. So if G is a lambda spectral, and the minimum degree of G is say, I'm not going to be terribly precise here, it just needs to be like some polylog or something like this, then this happens. Then okay.
Lambda is anything bounded away from 1.
So I need to tell you what I mean by spectral expansion. This is the spectral, lambda here is, for me, is the spectral gap. So like, this means if you looked at your adjacency matrix, the adjacency, like you got it normalized properly. This would have eigenvalue 1 and then 1 minus lambda. Okay.
But like what's lambda?
Constant lambda is fine. Lambda that's 1 over polylog is fine. We're going to lose something that depends on lambda and the number of constraints. So as long as lambda is like 1 over polylog, it's fine. If it gets smaller than that, you get in trouble because you start losing bigger factors in the number of constraints. Yeah. So you can prove this. Let me not do that because it's not very hard. You basically write LH. I'll just tell you the main thing. You write LH is the sum of these edges, the Laplacian of the individual edges, multiply it by like the random variable that determines if it's selected. You want to argue that this is like less than G, LG. So what you actually do is you rescale this by like LG to the minus 1/2, except you really need technically the pseudo inverse. You put that here. Okay, now you've got the sum of independent matrices. You just need a spectral norm bound. You use like matrix Chernoff or something. And you, okay, so this is not actually terribly hard.
So you will guarantee the LH is at most like half or less than half LG.
With high probability.
With high probability. Do you also get the left hand side?
You can get a lower bound too, but we don't need it.
Okay.
So can I say one line for people who have seen spectral specification? So one way to describe what Peter's claim here is that all the leverage scores of the edges are within 1/λ factors of each other. So, if you oversample as you do in spectral specification by 1/λ, you would get a spectral specifier. So it is basically like just a play on the classical Spearman-Srivastava proof of spectral specification.
Yeah, exactly. So in that proof, you like sample with weights according to the spectral norm of this matrix in here.
By the way, the two comes from this H density 1/2, is it?
Yes, yes, because I'm not normalizing things. Okay, so this solves the random case already. This says in the random case, I'm recovering X star exactly, because you just follow through the whole proof. If the hypergraph originally is random, this graph is random or like random enough that it's an expander. So therefore you have this condition. So therefore your SDP is giving you X star. So therefore you just read off X star and then you read off Y star and then you're good.
And you don't even need rounding.
Well, the rounding here is like you just look at X and you're like, oh, it's X star transpose, and you go home.
Yeah, you don't need to do this Gaussian rounding.
There's no Gaussian rounding, yes. Yeah, the rounding is, well, I mean, if you did the Gaussian rounding,
it would also work.
It would also just work with probably like the Gaussian rounding is like you sample a Gaussian that's like literally just X star. Yeah, okay. It's like a little bit silly to get. Yeah. Or like it's a Gaussian times X star. Like a one-dimensional Gaussian times X. So yes.
You get the Boolean solution. I don't know why you need to round.
You don't need to round. I'm just saying you could round with the Gaussian rounding, and it's like kind of trivial. Like it just doesn't.
Take your sledgehammer.
You want to distinguish -1 and 1, pick a Gaussian.
The nail is already in when you take the hammer and hit it.
Yep. Okay, so this, yes, solves the random case. The problem is, this doesn't work for semi-random, right? Like, I mean, my graph's not an expander, it's arbitrary. What do I do? Oh no, well, you use expander decomposition. It's actually not that complicated. It turns out that for a generic graph, you can decompose it into expanders, right? So if I have any arbitrary graph, here's my G, it's got some edges, I don't know what it is. I can always split it into like pieces. Each piece here is like a lambda expander, and I may have edges between the pieces, but I only lose like a little of one fraction of the edges here. Okay, so basically by discarding some small number of constraints, I can put it into this expander decomposition.
The many expander decompositions.
So there are, yes, so there are many of them. They all are like, I don't know, like some of them are trying to get like really fast, efficient ones. So I mean, the thing we actually used in the paper is really simple. It's like you just do Cheeger, like you just use Cheeger to find a cut and then split on that and to keep doing. Yeah. So it's not, you don't need anything fancy for, I mean, our algorithm is like
important that you don't mind if the spectral get small.
Yeah.
I think going smaller than 1/log n is not achievable.
No, but you don't, but 1/log n the cube satisfies.
Yeah.
So, yeah, it's not a very strong expander.
No, we don't need a very strong
That's why,
expander.
you know,
But for generic graphs, I don't think you can make them stronger expanders with composition. Like you will delete all the edges potentially.
The best expander you can embed inside an arbitrary graph, would not expect to get better than 1/log n. Is what Peter is saying. Yeah.
Sorry.
Like you had a question, right?
Oh,
No,
Your tongue?
this confuses me, so maybe
Okay.
walk me slowly. Everybody's understanding. You started with an arbitrary, but now you're saying I can do expander decomposition.
Yes.
So now, kind of, if you look back at your constraints, you like partition the variables in a way. So now you're trying to kind of, like, is it trivial why you can like recover X star back or something? Like what's
So you can't recover X star exactly. But I remember I said you can't do this in the semi-random case anyways. Right? In fact, I said in the semi-random case, you have to throw out some edges. Here are the edges I'm throwing out. I have to do this at some level. Like there is, in fact, that example I gave you on my slides is quite literally, you have a graph where one part is expanding and one part is like highly not expanding. And you just are giving up on the non-expanding part of the graph. Like it's literally in two components where one is expanding and it's like almost all the edges. The other is a very small number of edges and is not expanding.
Right. But okay, so like back to how the hypergraph looks like for every edge you're losing here, you're losing like you're just losing some constraint, and then you're looking at like some platinum solution.
Yeah.
Oh,
so right, I haven't told you quite how to get back to the original instance yet. So that's what I'm going to finally explain. Okay. So what this really allows you to do is take any 2 XOR instance, I partition it into these pieces. On each piece, I can recover X star exactly.
But it's X star projected on those variables.
On those variables only. In fact, there is a problem here, which is that I can't just try to like recover Y star in here and here and here and here and here separately. And it's because, remember my meta variables, right? It's like X is really like X sub like 2 variables, right? So if I had like X sub UV here, I could have X sub UW here, right? And remember I said you can like recover X exactly on each thing, but like up to a global sign. And I need to get the signs consistent across the pieces then, if I want to match these up. This is a problem. There may be really way more than like, you can't just brute force try all the pieces because.
You do know that there is a sign that's consistent because you are close to Y1 star.
Yes. So, but there may be like, way more than log n of these pieces. So you can't just brute force try all assignments either. Turns out there's a very kind of slick way to get around all these problems. So I'm not going to worry about recovering X star anymore. So that was my whole motivation. I'm throwing it out the window now. Instead, what I want to observe is that on this piece, because you agreed with X star, for every constraint in this piece, I've told you whether the hidden solution Y star, even the original 4 XOR instance Y star, agrees with the hyper edge that gave the edge that was here, or if it disagrees. I know exactly whether the constraint was noisy or not. Okay. So I can now actually completely forget about trying to use this anymore. I just use this to read off which edges were noisy. And what this means is my algorithm can do the following. Okay.
This is true only if like the whole constraint is in the part. I guess it's just the.
Yeah, but like almost all your constraints belong in one of these pieces, right? Okay, so what really I've done is I take my algorithm and my algorithm says for each C, you split it into one of 3 buckets, right? There's like the correct bucket, there's the noisy bucket, and then there's the like, don't know. Right, the correct bucket means you're declaring the right-hand side of the constraint to be consistent with your planted assignment. The noisy bucket, you're saying I declare it to be noisy. The I don't know is saying I don't know, and we are basically saying the number or the fraction C in the like don't know bucket is little o.
It's the edges across the.
These are the constraints that give the edges that cross the expanding. And so we're basically done. What I've said is that like, once I've removed all the noise from these constraints, I know which ones are in my don't know bucket. I throw them out, I remove the noise. I'm given a system of linear equations with no noise, and I can just solve it, okay, with Gaussian elimination. In fact, I've done something a little bit more interesting here, which is you think of like whether or not you could recover X star given all the equations unnoised with like no noise, right? That's some like subspace question. There's some linear subspace there, and X star, you can at least identify some subspace it lies in. You can think of each equation as like giving you some amount of information about X star. And what this says is that after throwing out little o of 1 fraction of the equations, I have all the information left. Okay. And as I've already justified, the little o of 1 discarding is like a necessary thing you have to do.
By the way, the 4 hypergraph you start with, it has n square edges. So you also have n square edges after you group those variables. So it's the dense graph.
Yes, it says average degree polylog n.
Okay,
There's an extra polylog in front
so
of
that guarantees the average, the smallest degree is.
degree is polylog, yeah. In fact, if the average, so if the minimum degree is small, you just like throw out all vertices with like minimum degree, like degree smaller than the average by like a polylog factor, and this discards a very small number of edges and fixes everything.
So does this mean like you can even work with like until 1.5 edges?
No, because then your minimum degree here will be less than one. Or your average degree will be less than one, so in
Oh,
particular.
I see. Yeah, okay.
Okay, so this is much stronger than that original goal I wrote, right? It turns out that this behavior is actually what we need to get the final reduction from a general CSP to XOR to work. Because what ends up happening is we produce all these different systems of linear equations. And what we actually do is we just take the constraints that I can denoise from each system, build like this huge, bigger system, and solve that. And we argue that a solution to that huge system of linear equations will actually then satisfy most of the constraints. And it's a lot trickier to actually execute this. And it's not like the very simple thing for random where you're just like, oh, it's X star, I had X star. That's the final thing I want to say just before we finish up here, is that the reason this doesn't give us the sub-exponential time thing is coming from the fact, like the 2 to the end of the delta, the full, that interpolation, is because when I try to do that, my matrices have size like 2 to the end of the delta. Now, here we are losing factors that are actually polylog in the size of the matrix.
Whereas here in the expander.
Like in this whole thing, like the expander decomposition, the lambda is 1 over log size of the matrix, for example.
Wait.
So this lambda here, right? I was saying with expander decomposition, you can take this lambda to be 1 over log size of the matrix. Size
How
of
did
number.
the matrices blow up to be exponential size?
So for this 2 to the end of the delta algorithm, that's just the size of the matrix. Like the runtime is basically the time it takes to compute the spectral norm of the matrix, which is like roughly the size or the polynomial in its size. Like this is the Kikuchi matrix where it's like the index.
Oh.
It's like the n choose L by n choose L matrix where L is like end of the delta. Yeah.
And you don't have special expander decompositions for these things?
Yeah, great question.
Great question. I think it's even false.
Well,
Kind of.
yeah.
The expander thing is false.
Yes.
Expander thing is false.
Okay. Interesting.
The sparsification statement is more intriguing.
And you need that lambda to be so low because of the little old one factor fraction or something? Like,
Yeah. If lambda is not like 1 over log size of the thing, this little o of 1 is not a little o of 1. It's all your edges. In fact, this is like you can make the little o of 1 like epsilon squared over like log squared size of the thing for lambda is like 1 over log.
Good.
There's some square root something coming in from secret.
In general, I think the number of edges to throw out looks like m times lambda times log n. So that's the information theoretic best bound. And then, if you apply, let's say ARV or Cheeger, then you lose additional log.
Sorry.
So just assume there is m lambda log.
Lambda is this, then the
Now
number.
lambda needs to be commensurately small.
The number of edges, sorry, I remembered our trade-off. Number of edges is epsilon m if lambda is epsilon squared over log squared. Size, and this is like size of your matrix, which for the polynomial time case, remember, is like n to the k over 2, so it's still log little one. But for the bigger case, this is a big factor loss. For the random case, we managed to get around all this by doing some like weird stuff with sum of squares. But that sort of thing, those sort of tricks don't actually work for the semi-random case. Okay. Pretty much out of time, so this is it.
Thanks for an excellent. A question or two?
Heckle me Wario Tom.
I think that was very.
You think?
All right, so questions over lunch.